Alright, this video is on intermolecular forces. Just to reiterate the reading that you guys did last week, um, intermolecular forces are the attraction of one molecule to another. So what we've been talking about with the covalent bonds, ionic bond, or sorry, the covalent bonds, polar covalent, non-polar covalent, those are both intramolecular forces that are having the attraction of like the opposing or the other nuclei. So for example, if I have um, let's say hydrogen and I had chlorine, right? These guys right here are going to form a bond, and within this molecule there are forces acting on each other, such as the attraction between the electrons in the nucleus, which have the protons in them. Okay? Well, these intramolecular forces are actually fairly strong. The polar covalent, non-polar covalent, those are very strong forces compared to intermolecular forces, which are like the attraction between one HCl molecule and another HCl molecule. Okay, so the attraction between these two would be an intermolecular force, versus an intramolecular force would be like the bonds that hold the atoms together. Okay? So, one thing we need to know, the strength of intermolecular forces are weaker than the strengths of intramolecular forces. So, bonds are stronger. All right? There isn't this little dotted line right here, the blue dotted line. That is not a bond, that's just an attraction. Okay? So, let's go ahead and take a look at the three different types of intermolecular force. Okay, the first is London dispersion, or just dispersion forces. Okay, you may just hear just London dispersion forces, or LDF. Okay, a little acronym for you. Okay, this type of intermolecular force is often going to be found between non-polar molecules. Okay, so if you have two nonpolar molecules, chances are the intermolecular force that's attracting and repelling them are going to be London dispersion forces, or LDF. Okay, the second one is dipole-dipole. Okay, dipole-dipole interactions, and obviously this would be between polar molecules. All right. Now the last type is, in truth, a dipole-dipole, but it's a special type of dipole, and they're called hydrogen bonds. Like I said, it's kind of confusing considering they're not bonds, but I'm calling it a hydrogen bond. Okay. Um, this is going to be between polar molecules, but they have a distinct characteristic. They must have a hydrogen on one of the molecules being attracted to either a fluorine, an oxygen, or a nitrogen. Okay, so I'll give examples of these, but a hydrogen having of one molecule being attached to another. Let's go ahead and draw a different color for this. So let's just say this is the blue is off one molecule, and the F, O, and A or N are off, say, a different molecule. They doesn't have to be on the same one. These could be three different ones, and I'll give you examples of them. But if you have two polar molecules, and a hydrogen on one of the molecules has access or exposure to a fluorine, an oxygen, or a nitrogen on the other molecule, it's going to form an attractive force. It's going to form a what we call a hydrogen bond. Now, hydrogen bonds are very important when it comes to our biology, because, believe it or not, parts of our DNA are actually held together by these hydrogen bonds. The A's, T's, C's, and G's that hold our nucleotides together, um, inside the rungs of the ladder, those are held together by hydrogen bonds. So let's go ahead and start talking about some examples of these different types of intermolecular forces. And the first one will be London dispersion, or LDF. All right? So if I was to take two nonpolar molecules, because this is going to be the attraction between two nonpolar molecules. For example, let's go ahead and say I had carbon dioxide. I had two carbon dioxide molecules. Here's one, and here is another. Okay? I'm just drawing them next to each other just to show things and be simple. But, you know, obviously I have more than just two CO2 molecules. They'd be all over the place. So here's CO2 and CO2. Let's go and let's call this CO2A and call this CO2B. All right? Now, we've all discovered that these bonds right here, these double bonds, are the sharing of 4 electrons, and because the difference of electronegativity between carbon and oxygen is a polar bond, right? But it just so happens that these two dipoles, this dipole right here and this dipole right here, are going in equal and opposite directions. Therefore, the entire molecule does not have a dipole. All right? Now, that doesn't mean that for an instant, okay, just for a second or a millisecond, okay, these electrons right here, these electrons right here, the two that are in there, the two that are in there, they are moving around. Right, let's fix that right there. All right, they're moving around, and there could be a time. Okay, I'm going to go ahead and zoom in on this right here. Okay, I'm going to go ahead and put this, make this guy big, right? Double bond, O, O, right? Let's just say we have, right now in this general area, we have 4 electrons, right? 2, 4, and then maybe 1 in here. Let's go and say 6. We have 6 electrons here inside the realm of oxygen. Well, it could be, for a second, since the whole molecule itself is nonpolar, there can be a tendency sometimes for electrons to be around the carbon more. Because in fact, remember, can't forget, this is a sharing of electrons. Yeah, they may be an uneven sharing, but that doesn't mean they don't share. Well, let's just say for a second, the 2 of these 6 electrons happen to be now over here closer to the carbon. And if they're closer to the carbon, that means just for a second, okay, like I said, this is very instantaneous, very light, okay, there could be more electrons over here than, say over here, right? Because remember, carbon right now has 8, but instead of the oxygen having all 8 of its, 2 of them, or say even 4 of them, may have gone over to be around the carbon, even if it's just for a second. Well, at that moment, there's now more electrons around carbon than there is around oxygen, okay? And because that happens, we can end up having a what we call an induced dipole, or an instantaneous dipole. It's just for a second. Now, all of a sudden, this side over here becomes slightly negative, and this side over here becomes slightly positive. Remember, it's a nonpolar molecule. These slight charges are going to be here and gone. Okay? Okay? They're here and gone. But for just a second, we have a slight negative on this side and a slight positive on this side. Remember, I was just referring to this oxygen. This oxygen over here, he might be doing just his normal thing, and they're sharing electrons unevenly, which means there's even more electrons to the right. So just for a second, we have a slight negative charge right here and a slight positive charge right here. Okay, think about it. What's that going to do to this other molecule? Okay, what that's going to do is it's going to repel all the electrons that are underneath, or that are around this oxygen, and it's going to push them over to the side. Okay, and which now would make this molecule slightly positive on this side and slightly negative on that side. Okay? But like I said, this right here is a very quick process, and it doesn't last very long. Okay? It can just, for a second, all of a sudden, the carbon has more electrons than it normally does, which means that's the right side of the carbon dioxide molecule may have more electrons, and which means just for a second, that has a slight negative charge. And what that means is, obviously, then the other side of the molecule would have a slight positive charge. All right? So that would is, and the attraction between this slight negative and that slight positive of these two particular molecules is called a London dispersion force. This attraction of this negative right here and that positive right here, even if it's really, really short, that is an attraction, and that's going to be a London dispersion force. All right? Now, the other two are actually quite simple, because this is kind of the harder one to wrap your mind around. All right? So now with dipole-dipole, let's go ahead and take hydrogen chloride and hydrogen chloride. Okay? Well, they already have, they don't have to worry about the slight chance of electrons wanting to be on one side or the other. That's already the way it is, right? Because we have a dipole, which means this side of the molecule is already slightly positive. This one's already slightly negative. This one's slightly positive. This one's slightly negative. And like I said, because that, obviously if that bond's polar and there's only one bond, that means the whole molecule itself is polar. Okay? You'll have an attraction right here, and it will be longer lasting than the London dispersion attraction. And because it will, A, happen more readily, and B, last longer, it is stronger. So what we know so far is that dipole-dipole is stronger than London dispersion forces. Okay? Now the last one, like I said, it's just a type of dipole-dipole, and that is hydrogen bonding. Hydrogen bonding is if I have, say, HF and HF. Okay? The fact that I have two polar molecules, right? They're going that way, and my bond polarity, if you guys wanted to put them in there, you didn't necessarily have to right, for this one. Okay? But I have, obviously, two dipoles going in the same direction, which means this is going to be slightly positive, this is going to be slightly negative, slightly positive, slightly negative. Well, as it so happens, when hydrogen, which is usually slightly positive, is going to come in contact with either nitrogen, oxygen, or fluorine, it's going to form a very strong intermolecular force. And the reason why it's so strong is because the electronegativity values of fluorine, 4.0, oxygen, 3.5, and nitrogen, 3.0. Those are very high electronegativity values, and they don't have many energy levels, so they're really, really small atoms to begin with, which means they're closer to the nucleus and all that good stuff. So because of these high electronegativity values and the fact that they're relatively small atoms, this attraction right here is crazy strong, okay? Which makes it the strongest intermolecular force, all right? But it's nothing more than just a type of dipole-dipole. So, in summation, we have hydrogen bonding, okay, which is a dipole-dipole interaction between a hydrogen and a fluorine, or a hydrogen and oxygen, or a hydrogen and a nitrogen. That intermolecular force is much stronger than dipole-dipole, which is still an attraction between two polar molecules, but they're not going to be having that hydrogen, oxygen, hydrogen, nitrogen, hydrogen, fluorine interaction. And of course, both of them are stronger than London dispersion forces. All right? So, if you guys have any questions on this video, make sure you guys either A, email me or ask me in class.